Okay, I think we will get started. Thank you everybody for coming. I really appreciate it. My presentation is going to be about a half an hour. If I do run over and you have to leave, feel free. My name is Paul Bedard. I've been a mathematics professor here at SC4 for about 25 years. And I wanted to offer this session, obviously in honor of Black History Month, but also because I absolutely love the history of my subject. I'm not a historian or a history teacher, but I'm fascinated by history, and I think it's particularly important to talk about scientists and mathematicians who are from diverse or underrepresented populations. So this includes women in mathematics. So next month, for Women's History Month, I hope to do this again. One of the great things about science, and particularly math, is we care about results, right? So in the past, when people weren't allowed to do things because of their identity, because of how they identified, because of their race, background, gender, ethnicity, we were missing a lot of results. We were missing a lot of good information that we could have had. But one way that those barriers were broken down was by the fact that mathematicians and scientists tend to care more about results. So they might look at you at first and say, you're not allowed to participate with us. You can't play our game because you don't look right or sound right or speak the right language or have the right beliefs. But as soon as you present results, that's the ultimate argument that answers all objections. I really went down a rabbit hole when I was researching Black American mathematicians. First of all, I didn't know how many famous mathematicians were African American. There's a lot. So I recommend that later you just Google African American mathematicians, and a drop-down list will come, and just have fun, pick any name and study it. I picked 4 particular people. And as I was studying each of them, I couldn't help but notice the things that united them, the things that made them different. One of the mathematicians I'm going to talk about, his mother was a homemaker, and his father worked on the railroad. So they didn't come from an academic background at all. And I wonder if he was really the first person in their family, if his accomplishments in academia were just unheard of to them. Another one, Euphemia Haynes. Wow, I really want to study more about this because her father was a dentist and she was born in Washington, D.C. And her family was part of the Black 400. And I had never heard of that before. Has anybody heard of the Black 400? There were 400 families in Washington, D.C. Now, if you know anything about demographics within our country, you know that Washington, D.C., which is our capital, also has a very large African American population. And it has from early days. And so some of the oldest families and the most well-respected African American families lived in Washington, D.C. So the Black 400 was kind of like the aristocracy among African Americans. They were the people at the top, the sort of the famous, well-respected, wealthier people within that classification of African Americans. They still dealt with racism, but they were insulated and shielded from some of the worst effects of racism. So Euphemia Haynes was the child of somewhat of privilege, but also not, because being Black in America came with a lot of issues. That was one rabbit hole I went down. Another one I went down was, again, looking at Euphemia Haynes. I was very proud for a moment, and then I was ashamed, and then I was sort of proud again at the way history changed, and it really made me think of what's going on in our country right now. Euphemia Haynes was the first Black woman to ever get a PhD in math in the United States. And she got that PhD in 1943. That really actually surprised me. because we tend to think of numbers like 1943 as being so long ago, and in times when racial equality was not anywhere near what it would later become. And she got it from a college called the Catholic University of America. She was actually honored by the Pope, who is the leader of the Catholic Church. And when I read that, I was very personally proud, because we all have our own identities, right? So my identity is Catholic. And I'm very proud of that identity. And I know that the Catholic Church has done some terrible things, but they've done some great things too. And I thought, this is really remarkable that this Catholic university was the first university to award a PhD in mathematics, of all things, to a black woman. So I went down that rabbit hole, and I was immediately proud and then disappointed. Because in the late 19th century, in the late 1800s, Catholic University of America was already accepting black students, which was unheard of at the time. They were way ahead of the curve. But then, segregation and racism in the country overtook them, and they started to feel like, we can't do this anymore. And they stopped. And around 1914, they stopped admitting black students. What a shame. What a terrible thing. And it made me think about a lot of institutions in our society today that are stopping or pulling back on efforts toward diversity and inclusiveness. And Catholic University, so I was briefly proud, like I'm a Catholic, we did the right thing, and then bam, disappointed, but then proud again. Because in the 1930s, I think it was 1936, right before Hitler started his nonsense, they started accepting black students again. And then as early as 1943, awarding Euphemia Haynes PhD. I also found her name interesting, and I'm going to talk about names. Her name is Euphemia, but actually she was born Martha. Martha Euphemia Haynes. And she liked Euphemia, so she went with that. Another of the mathematicians I'm going to talk about, his name is Albert Baruka Reed. And I thought, Albert sounds to me just like an ordinary sort of name that I hear of, and Reed, it's a pretty common name in America. But Baruka sounded unusual. Well, it turned out that was his wife's name. He hyphenated and added his wife's name to his name, which I think is remarkable. Both of these two people that I've talked about, Euphemia Haynes and Albert Baruka Reed, fought against segregation. Euphemia Haynes in particular fought against a system in schools called a tracking system. In America, we typically don't deal with tracking systems in the early grades. When you were in 6th grade or 7th grade, nobody said, you're not college bound. You're not college material. We're going to put you in these lower classes. And once you're on that track, you can never go to college because you're not being prepared for it. We try to prepare every kid for college. And that, by the way, is the reason when people say the United States is so low in education in the world, we could do a lot better, but one of the reasons is because a lot of places in the world do tracking. They take the kids that aren't doing as well at a very young age and they track them right out. So they're not being counted, whereas in America, we try to prepare every kid for college, whether they end up going or not. So Euphemia Haynes took aim at this tracking system because it was racist. Because black kids were more often tracked away from college. And so she wanted to put a stop to that. So as I've said, I'm not a historian, I'm a mathematician. So even though I went down these interesting rabbit holes, I really want to talk about the mathematics that these individuals contributed. And boy, let me tell you, that was hard. Because these were some really, really smart people, and I don't want you guys to feel less smart. I'm sure you're all brilliant people, I know, because you chose to be here today. That's all I need. But they did some really smart stuff that was really hard for even me to understand. And when I finally understood some of it, I thought, how am I going to bring it to a level where everybody that might come to my talk would get something out of it? So I think I've succeeded, but you'll have to let me know if I did. So we're going to talk about David Blackwell first, and I've written just a few things about him here. All of this, by the way, is plagiarized. It's not plagiarized because I gave the source, but I didn't rewrite it. It's all just quotes. He served as president of the Institute of Mathematical Statistics, vice president of the American Statistical Association. I'm teaching statistics right now, and I wanted to favor my own class a little bit. He won the John von Neumann Prize. One of my mathematicians was friends with von Neumann. I think it was Blackwell. And they chatted, and von Neumann wanted, if you don't know who John von Neumann is, he's an absolutely brilliant mathematician. And they chatted, and von Neumann asked him to read his doctoral thesis. But David Blackwell was responsible for something called the Rao-Blackwell theorem. I assume I'm pronouncing Rao correctly. And I'm going to talk about it in just a moment, but first I'll say that I was afraid somebody would say, who was Rao? And I don't know. So I looked that up and I thought, well, boy, Blackwell is our black mathematician. I bet Rao was some white guy that tried to steal credit. Nope. Rao was C.R. Rao, and he was an Indian American, not native indigenous Indian. Indian from India in Asia, an Indian American mathematician. So those two got together and came up with this theorem. So I'll read the statement of the theorem, and then I'll try to bring it to where maybe we can all get something out of it. And I got this from the website of Wolfram Math World, which I highly recommend for any math question you have. Go to Wolfram Math World. The Rao-Blackwell theorem states that for a given estimator, taking its conditional expectation with respect to a sufficient statistic always produces an estimator with a lower variance, meaning it is a more efficient estimator. Essentially, it provides a method to improve an estimator by conditioning it on a sufficient statistic. What does any of that mean? An estimator is a simple formula that we use to determine the probability, the likelihood of something happening. I did not know how many people would show up for my talk today. I'm thrilled because the room is essentially full, so I don't feel like it's an unpopular talk, but I didn't have to turn anybody away. This could not be more ideal. But my two concerns were that I would be giving the whole talk to Janice, Dr. Fritz sitting in the back, because I knew she was coming, because we're friends. That was one concern. The other concern is that I'd be flooded with hundreds of people. How could I determine how many people would be likely to come? What would be a sufficient statistic? A sufficient statistic, simply put, is some number, some data, some measurement that I have that would give me some decent idea of what to expect in the future. If I had given a Black American Mathematicians talk in February every year for all of my 25 years at SC4, and I had all that data, that might very well constitute a sufficient statistic. I could use that information to estimate, right? I could say back in 2012, 15 people showed up, and the next year 17 people, and the next year 20 people. And based on that, maybe I take the average of all those numbers and say that's what I'm expecting. Maybe I take the maximum of those numbers and say it's been increasing, so I'll take the maximum and then add 2 to take into account increase. And maybe that's what I'm expecting. These little formulas or tricks are called estimators. And what Rao and Blackwell did was amazing, because it says for a given estimator, so let's just pause there, a given estimator, any estimator, no matter how stupid it is, you can Rao-Blackwellize it. I did not make that up. You can Rao-Blackwellize the estimator and get a good estimator. from your sucky, stupid estimator. And I'm going to show you the process of how that happens. So the stupid estimator is usually called delta 0. And the Rao-Blackwellized better estimator is called delta 1. So, rather than talking about how many people show up to my talk, I'm going to do something with smaller numbers. How many people show up to my office hour? I have a conference hour that students are welcome to, and it is not a widely subscribed event. Very few people come, and that's fine. But suppose I had kept track over the last 5 office hours of how many people came. We're going to say X is how many people come to my office hour. X is called a random variable. And we're going to talk about random variable because I did have a theme connecting these mathematicians. So you have to know that a random variable is a variable that the value can be different. It's random. So if I said take a quarter out of your pocket and flip it 10 times and count how many heads, that's a random variable. Because it could be no heads, 1 heads, 2 heads, 3 heads, all the way up to 10 heads. It could be any of those values. It's more likely to take some values than others. You're more likely to get 5 heads out of 10 than you are to get 10 heads out of 10. So that's called a random variable. So if X is my random variable for how many people, then I'm going to call my first office hour X0 rather than X1 so it reminds you of D0 over here. So X0 is my first office hour. X1 is my second office hour, and so on up to X5. Have I lost anybody yet? Anytime you need a joke to break the tension of math, if the math tension is building in you to the point where you think you're going to explode and you want a joke, I can tell one. Like for instance, today, this is not even a joke, but today in my statistics class, we randomly talked about bovine diarrhea. We did. All right. So, suppose I know the values of X0, X1, X2, X3, and I did actually originally say the first 5, so, and X4. So all I'm saying is that that random variable of X takes on different values each day. And the first office hour, nobody came. The second office hour, 1 person came. The third office hour, 1 person. And then 2, and then nobody came. Using this information, I want to form an estimator, some sort of formula, some sort of technique for predicting my office hour tomorrow. How many people will come? I could do a lot of things. I could take the average of those numbers and round it to the nearest person and say that's how many are likely to come. I could take the highest number, 2, and say 2 is what's likely to come. I can do whatever I want. But we're supposed to come up with a probability. What is the probability of, let's say, the probability that nobody comes tomorrow? So we want to find out the probability that my next office hour, nobody comes. And we're going to use an estimator. D0 is going to be an estimator. It's the given estimator, the original one, and it's going to be crappy. It's going to be a terrible way to figure this out. That's it. That's my estimator. My estimator for the probability that nobody comes to my office hour is a 100% chance that nobody will come to my office hour if nobody came to my first one. Or a 0% chance that nobody will come if anything else in the world happened. So based on this data, because nobody came to my first one, I'm now saying there's a 100% chance that I'll have nobody tomorrow. Do you agree that that's a pretty crummy estimator? Historically, it looks like I get people more often than not claiming that there's a 100% chance that nobody will come. Imagine if I just didn't show up. Somebody called and said, Bedard, you're supposed to be in your office hour. And I said, no, I used math to prove nobody would show up. And they said, there's 3 people waiting for you. And I'm like, I don't know what the numbers don't lie. I can tell you. It can't be there. But that's called an estimator. And it's crummy, but this is what makes math so fascinating, because math takes things very, very explicitly and specifically. This Rao-Blackwell theorem says any estimator, it doesn't matter how crummy it is, if you do a procedure to it, you can get a better estimator. I went through the procedure, it's lengthy. So this type of random variable is called a Poisson random variable. It's distributed according to what's called a Poisson distribution. So the Rao-Blackwell theorem tells us that our next step is to find a sufficient statistic, some piece of information that will help us make this estimator better. And the sufficient piece of information, the sufficient statistic, is the sum of all of those numbers. It turns out that everything that is important to know for this process, we can get from the sum of all those numbers. And if you start with this crummy estimator, and you only add that fact, the sufficient statistic, you get this estimator. Now that's a formula that some of you might be not super comfortable with. But that basically says n is the number of office hours that I looked at. I looked at 5 different office hours. 0, 1, 2, 3, and 4. So n is 5. And Sn is the sum of all these numbers, which is 4. So 1 minus 1/5 is 4/5. And 4/5 raised to the 4th power is 0.4096, or about 0.41. So what we've shown is that according to the new superior estimator, more efficient estimator, there is about a 41% chance that nobody will come to my office hour tomorrow. Much better. Based on the data, that seems reasonable. We can even see that of the 5 office hours I have, 2 of them nobody came. That's 40%. That isn't why we got 41%, but it sort of matches this data pretty well. So that's what Rao and Blackwell came up with. That is tremendously important. That is a result that scientists can use, that people can use. And if I told you that a black guy came up with it, your first thought would maybe be, I liked it already. It didn't really matter to me. And if I told you that an African American and an Indian American came up with something, hopefully you wouldn't say, I'm not interested because of their identity. You'd say, show me the money, show me the results. And let's see what they did. And by the way, just for any advanced math people out there, the Rao-Blackwell process is idempotent. Idempotent means same power. Idem is same and potent is power. Idempotent is when all iterations of something are the same. What it means is that if you take that second, that D1 estimator, and you Rao-Blackwellize it, it'll be the same. Which is super important. Can anybody think why that idempotency probably made Rao and Blackwell really happy? Because it shows it's a pretty good estimator, doesn't it? Because if every time you did the process you got a different estimator, you would not have a lot of confidence. You'd say, we better do this 5 million times and then we're still not sure. But this shows that this is a really, really good estimator. Does anybody have any questions about the Rao-Blackwell estimator? Okay, then I'm going to move on. J. Ernest Wilkins entered the University of Chicago in 1936 at the age of 13, becoming one of the youngest students to ever attend that university. J. Ernest Wilkins, I put in here, it has nothing to do with statistics, but he worked on differential equations, which I absolutely love. And he worked on particularly generalizing the results of, oh my gosh, I'm almost out of time. I was going to write one up here, but I'm running out of time and I want to say other things. He generalized the results on linear differential equations. Email me if you want to know how that plays out. Euphemia Haynes we've talked about. I want to talk about Albert Barucha Reed because I promised Dr. Fritz that my talk would have something to do with biology, and it does. And this ties back into random variables. So I'm going to quiz you biologists. This is a mathematical formula from biology. And I will give you one hint, because we sometimes use different letters for different things. And when I was researching this, I found about 3 different letters that people use for this. So this Greek letter lambda is called the modulus of elasticity. It shows how elastic something is. So for instance, iron has a lambda of 21. It's not very elastic. Aluminum is 7. Bone is 1.6. Human bone and human hair is 1.0. So the higher lambda is, the less elastic the substance is. Now, would any biologist out there like to take a guess what that formula is telling us? All right, I'll give a couple more hints. F is force. A is cross-sectional area. Delta L is change of length. And I don't know why the bottom one says delta L0. It should just be L0. There can't be a change in the original, because it's the original. L0 is the original length. Delta L is the change of length. Any thoughts? Well, I would not know either. This is a formula to determine the force on a tendon. If the tendon is stretched out of its ordinary length, then you multiply by the modulus of elasticity, the cross-sectional area, and the ratio of the change of length to the original length. So biologists and other scientists use these formulas all the time. But what did Albert Barucha Reed add to this discussion? Lots and lots of math formulas, like potential energy is mgh E is equal to mc squared. A lot of formulas have constants in them. A constant is a number that never changes. You just memorize the value of it. But what Albert Baruch Reed realized was we get these constants from measurements. The modulus of elasticity is not actually a constant for human bone. We measure the elasticity of various human bones, and we sort of take the average, and we call that the constant. The speed of light is not a constant. In different media, it changes a little bit, and our measurements can be inaccurate. This is gravity. Gravity changes depending if you're standing on a hill. And again, your measurement of it can be inaccurate. So, what Baruch Reed decided was that these constants should not be constants. They should be random variables. Because then we can import the entire science of statistics. So a random variable doesn't mean that modulus of elasticity can be anything. It doesn't mean your bone suddenly is as elastic as a piece of rubber. It's not. It means there's a distribution, like the Poisson distribution, or the binomial distribution, or the normal distribution. And within that distribution, the value of the constant has a certain probability of being one value or another. So we can refine our formulas and make them more like our ever-changing real world. And here's just some other examples. The diffusion coefficient, the propagation coefficient. And this is a quote from Baruch Reed's book. Mathematical equations play a central role in all branches of the applied mathematical sciences, and coefficients and parameters are experimentally determined. And I think that's a good place to wrap this up, because that really started my brain thinking. Everything that we assume is constant and fixed and absolute and unchanging is a random variable. It shifts. It changes depending on all sorts of factors that we can't necessarily control. And the same is true in our society as we look at people with different identities and the rights that they have and the recognition that they receive. And we think that some things are constant, that will never change, right? A lot of people thought Roe v. Wade, the abortion law, would never change. I'm not saying it's good or bad. I don't want to get into a debate, but people thought that's forever. It wasn't. Nothing's forever. We're living on shifting sands of things changing. But we can have some control over it if we're able to have a predictor, and if we're able to refine our predictions when we get some new information, sufficient information, so that we can have some control. We can predict this modulus of elasticity won't just change your bones into rubber. You can have some understanding if you understand the mathematics behind it. So I encourage you to look up all four of these mathematicians and read more about them. Their life histories are fascinating. I only touched the surface. There's so much more that I could have said about each of them. The Black 400 in Washington, D.C., research that, Catholic University of America, and all of these other topics. And thank you so much for coming. I really appreciate all of you. Thanks.